All right, so far we've been drawing our Fisher projections as linear molecules. However, in real life, these carbohydrates actually exist as cyclic structures. And remember, back in organic chemistry, we know that 5 and 6 membered rings are going to be favored. So let's go ahead and take a look at how we're going to convert our linear structures into our cyclic structures. So the first thing that we realize is that we have alcohols, which are good nucleophiles, and then we have carbonyls, which are good electrophiles. And so what we can have is we can have a alcohol attack our carbonyl, and then a proton transfer occurs to get what's known as a cyclic hemiacetal. And so what we can see is we have our 6-membered ring. The hemiacetal basically means that one of the oxygens is like an ether and the other one is like an alcohol. So let's take a look at an example of D-glucose, and I'll only ask you to do 6-membered rings. We won't do 5-membered rings. And this will probably be the trickiest part of the carbohydrate section. Again, we're not going to go very deep into this. Biochemistry is not my specialty. And to be honest, I've forgotten most of this, so it's been interesting relearning it. So anyways, D-glucose, it's an aldose, hexaldose. So we have an aldehyde and we have 6 carbons. In this case, we're going to go for D-glucose. So we know that this last OH is pointed to the right side. As for the rest of the OHs, we're just going to copy that from somewhere else. Or, you know, if you're taking a biochemistry course or our biochemistry major, you can go ahead and just start memorizing these things. A lot of memorization in biochemistry. So anyways, we're going to want to form 6-membered rings. And then if we count our carbons, we have 1, 2, 3, 4, 5, 6. We have 6 carbons there. But let's take a look at our structure up here. What we notice is that we have an oxygen inside our ring. So we can't have 6 carbons there. We can only have 5. So what's going to happen is this oxygen right here is what's going to do the ring closing. That way we end up with a 6-membered ring. And the way that we're going to draw these is through the shortcut way. If you'd like to be, draw it from the linear structure and follow kind of a more logic-based path, you can go ahead and do that. I highly recommend these articles from Mass Organic Chemistry, the Hayworth projection, and then of course, converting a Fisher projection to a Hayworth and vice versa, which is kind of what we're going to do here in a second. But first, we're going to change them into our chair structures from organic chemistry, since we're organic chemists. And by convention, we put the oxygen in the top right. So that's going to go ahead and go like so. By convention, this is going to be carbon number 5, 4, 3, 2, 1. All right, so we can see that we have carbon number 6 is not going to be in our ring, and it's going to be coming off of carbon number 5. Just draw that a little bit better. And so what carbon number 6 does depends on what kind of sugar you have. For the D sugars, carbon number 6 will be pointing up. For the L sugars, carbon number 6 will be pointing down, right? We've got a D sugar because this OH is on the right side. So we're going to have carbon number 6 point up. And so if we insert carbon number 6 in our structure, pointing up is in this way. And what you can tell here is that it's in the equatorial versus the axial position, right? That may have something to do with the fact, or that may be partially the reason why we only see D sugars. Remember, the equatorial position is more stable, right? So there's carbon number 6. And then the rest of it really isn't too bad. Any OHs that show up on the left side over here are going to be in the up position. So off of carbon number 3, we've got an OH in the up position, which if we think about our cyclohexane chair, which you may have to review how to draw these, this is going to be in the equatorial position, which is going to be favored. Any OHs on the right side other than, the OH that's going to make the bond is going to be in the down position. So carbon 2 and 4 are in the down. So if we look at 2, down would be pointing this way, which is the equatorial position as well. And then carbon number 4 is also pointing down, which is, again, the equatorial position. So very, very cool there. All right, now we just have to think about what's coming off of carbon number 1. What's coming off of carbon number 1 is that oxygen, which then proton transfers to become an alcohol. And the carbon directly attached to it is called the anomeric carbon. And then I'm just going to go ahead and take this and copy it down here. All right, and so what we can have are 2 different what are called anomers, right? So we're going to label these as anomers to one another. And then one is going to be the alpha and the other one is going to be the beta. So this one is going to be our alpha anomer, and this one down here is going to be our beta anomer. In the alpha anomer, the carbon number 6 and the substituent off of carbon number 5 and the alcohol off of carbon number 1 are going to be on opposite sides. So since this one right here, number 6, is in the up position in the alpha anomer, it's going to be in the down position. So this OH is going to be pointing down, right? Or axial. In the beta anomer, they're going to be in the same position, right? So since carbon number 6 is pointing up, the alcohol coming off of carbon number 1 is also going to point up. In this case, now the equatorial position. And so if you think about which one's going to be favored, this lower one's going to be favored because it has everything in the equatorial position, whereas that top one has one in the axial position. But they are free to open up these chains and then reclose them, right? So they can go from the alpha to the beta and anomer just fine. And this is one of the reasons that glucose is the most common sugar. You can tell in this beta anomer, it's very stable because everything is equatorial. If you draw the structures for the other sugars, you'll notice that some of them must be, axial and not equatorial. Cool. So that's how we draw it in organic chemistry. And I'm going to just draw it down here one time as well. All right, so that's our chair structure. The other way that we can draw these are the Hayworth structures or the Hayworth projections. And so this is more common in biochemistry. They don't like drawing the chairs like this. They don't really care about the conformers, and they just do it in a different way. It's actually an easier way, so not too bad for us. We're just going to draw a hexagon with the oxygen in the top right corner. And then we're just going to point things as up or down, right? So we can see that this carbon number 6 is up, this alcohol is up, and this alcohol is up as well. And then let's just go ahead and number them. See, we have this one as 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and then 6 will be pointing up there, right? And so everything that points up points, well, up, right? So there's that one pointing up. Off of carbon number 3, we're pointing up, and then off of carbon number 1, we're pointing up, right? So you can see that it still demonstrates the same information. It actually only tells you whether things are up or down. It doesn't tell you whether things are axial or equatorial. And then the other positions, right? This one's down and this one's down. So we can draw them as pointing, well, down, right? So this one's pointing down. And then off of carbon number 2, it's pointing down as well. Sometimes you'll see the other side drawn. So for example, maybe you'll see these other sides drawn. Sometimes there'll be H's there. Sometimes there won't be H's. That does not imply that there's a carbon here. It still implies that there's an H. It's just a different convention. I prefer just to not draw the other line, right? But you can see how they're showing you the same thing. This one's a little bit more clear in terms of what's up or down, but it doesn't tell you what's axial and what's equatorial. And remember that axial and equatorial and up and down are not the same thing. We can have 5-membered rings as well. I won't really ask you to draw any of those, but they're not too bad either. Remember that we have another convention we can draw our cyclic compounds, is we can just draw them as flat, and then we can determine up or down as wedges or dashes. So this is beta D ribose. Right, it's beta because the anomeric and then this kind of methyl then alcohol are pointed in the same direction. And the way that we would draw the Hayworth projection there is essentially the same thing, except instead of wedges or dashes, things are just going to be pointing up or down, right? So those two are pointing up because these are wedges, and then these two down here will be pointing down because over here they're dashes. Again, biochemistry is just an absolutely huge topic that spending, about a third of a semester on it doesn't really do it justice. And I don't want to just teach you a bunch of random things that you're going to forget. So basically, the main thing that I want you to be able to do is to just be able to go from a Fisher projection to our cyclohexane chair conformer and the Hayworth projections. So take a look at the work along. If you can do that, you'll be fine.